This lesson explores the concept of angular momentum, which is the rotational analog of linear momentum. We've already learned about the Newton's laws. The sum of the forces equals mass times acceleration, for example. We said that that's like torque. In rotation, the sum of the torques is equal to the moment of inertia times angular acceleration. We learned about kinetic energy and rotational kinetic energy. And now finally, if you remember what we studied after we learned about kinetic energy, we learned about momentum. Momentum was useful because if the net force on a system was zero, then there couldn't be any change in momentum of the system. Momentum was conserved if the net force was equal to zero. Well, there's a rotational analog to momentum. We call it angular momentum, and we give it the symbol capital L. It is equal to I, which plays the role of mass in rotation, times omega, which plays the role of velocity in rotation. Just like with linear momentum, angular momentum is useful because if the net torque on a system is equal to zero, then angular momentum must be conserved. It cannot change. Okay, we used linear momentum to solve problems that otherwise would have been hard to solve. Problems like collisions between two cars, or problems such as determining the velocity of a bullet when it leaves a gun. Angular momentum can also be used to solve certain problems in a way that otherwise would be very difficult to solve. So let's just start right out with an example. Okay, let's say we have a kid on a merry-go-round. So here's our merry-go-round. And let's say that this merry-go-round is starting out with an angular speed of, say, 1 turn per second. And there's a boy who's standing out here 2 meters away from the center on the edge of the merry-go-round. 2 meters. Okay, let's say that the mass of that boy is 50 kilograms. And let's say that the mass of the merry-go-round itself, the big platform, is 100 kilograms. Okay. Now, let's say that this boy decides he's going to walk to the center of the merry-go-round. Well, when that happens, the speed of the merry-go-round will change. And I want to know by how much. What is the new angular velocity? Now, if we consider the boy and the merry-go-round to be the system, then there's no net torque on this system, right? Because nobody's going to push the merry-go-round or anything, so there are no torques acting on the merry-go-round and the boy. Therefore, angular momentum must be conserved. So the angular momentum before the boy walks to the center must equal the angular momentum after the boy walks to the center. before the boy walks to the center, we have an angular momentum of I for the merry-go-round times omega for the merry-go-round plus I for the boy times omega for the boy after he walks to the center. We have I for the merry-go-round times the new angular velocity of the merry-go-round plus the new moment of inertia for the boy times the new angular velocity for the boy. Okay, now first of all, the angular velocity of the merry-go-round and the boy have to be equal to each other because the boy is on the merry-go-round. So if the merry-go-round is turning at 1 turn per second, then the boy is also turning at 1 turn per second. So I don't really need those subscripts on the angular velocities. Let's get rid of them. Okay, because before the boy moves, we've got the same omega. After he moves, he's still on the merry-go-round, so I don't need those subscripts either. And now we can start plugging in numbers. The moment of inertia of the merry-go-round. Well, I know the mass and the radius of the merry-go-round. I need to decide what shape I should use. So I think a merry-go-round is sort of like a disc or a solid cylinder. So you should look up in the table somewhere on the internet or your textbook, what's the moment of inertia of a solid disc rotating through its center? And you'll find that it is 1/2 mr squared. So moment of inertia of the merry-go-round, 1/2 m. Mass of the merry-go-round is 100 kilograms. R, the radius of the merry-go-round, 2 meters squared. So this is the moment of inertia of the merry-go-round. The angular velocity of the merry-go-round before the boy walks to the center is given in the problem as 1 turn per second. Okay. Plus the moment of inertia of a boy. That's a hard one. If you look up a moment of inertia of a boy on the internet or in the table in your textbook, you won't find it. So what should we use? Well, compared to the merry-go-round, the boy is small. In fact, we can consider the boy to have his mass essentially concentrated all at the same spot. Because his mass isn't really spread out over the entire platform. It's appropriate to consider the boy's mass to be concentrated at a point. And you will find in the table or in your textbook the moment of inertia of a point mass, which turns out to be the mass of the object, m, times the distance of that object from the pivot point, in this case 2 meters. So the moment of inertia of the boy will be the boy's mass, 50 kilograms, times the distance that the boy is away from the center of the platform, 2 meters squared. Okay, so that is the moment of inertia for the boy. He's on the merry-go-round, so he also is turning at 1 turn per second. That must be equal to the moment of inertia of the merry-go-round after the boy moves. Well, the merry-go-round didn't change any, the merry-go-round itself, so its moment of inertia is still 1/2 times 100 kilograms times 2 meters squared. the same quantity that it was over on the left side of the equation. The new angular velocity of the merry-go-round is what we're trying to find, plus 0, because the boy has now moved to the center. If the boy moves to the center, then his distance from the center is equal to 0. And since the distance from the center is in the moment of inertia equation, the moment of inertia of the boy after he has moved to the center is equal to 0. All right, well now we have only one unknown in this equation, and that's omega prime, so it's just a matter of plugging the numbers in. I'll erase the top of half of the screen so we have some more room to work up there. Okay, 1/2 times 100 kilograms is 50. 2 squared is 4, so we have 50 times 4, that would be 200. 200 kilogram meters squared turns per second. It's a weird unit, isn't it? A kilogram meter squared turn per second. Okay, plus 50 kilograms times 2 squared, that's 200. Oh, also 200. 200 kilogram meters squared turn per second equals 1/2 times 100 is 50 times 2 squared, 4. 4 times 50, 200. 200 kilogram meters squared turn, or no, not turn per second, because now I'm going to multiply by omega prime, and that's what I'm solving for. So if I add 200 and 200, I get 400 kilogram meters squared turns per second. Now let's divide both sides by 200. Kilogram meters squared. So kilograms cancel, meters squared cancel, and I end up with 2 turns per second equals omega prime. And we're done. The new rotational velocity of the merry-go-round is 2 turns per second. It got faster. This is something that you've observed before. Well, first of all, if you have access to a merry-go-round, try this yourself. Go around, spin yourself up, jump over up on the platform, and then move to the center of the platform and notice how the speed of the merry-go-round increases in order to conserve angular momentum. But even if you've never been on or seen a merry-go-round, this is something that you are familiar with if you've ever watched the Winter Olympics or ice skating. You know that when an ice skater goes into a spin, have you ever noticed how they always stick their arms out and their legs out as far as possible, at least one leg? They stick their arms and one leg out as far as possible when they go into their spin. Then what they do is they pull those arms and that one leg in. As they do that, their moment of inertia gets smaller. In order to conserve angular momentum, their angular velocity gets faster. So you've all seen that when the figure skater goes into the spin, they stretch out, and then when they pull their arms in, they speed up. That happens because of conservation of angular momentum.